This is the higher tier paper 1 GCSE Physics 2023 paper. And we're running through this paper today. Our first question on transformers. Figure 1 shows how the national grid connects a power station to consumers. Complete the sentences. Transformer X looks like a step-up transformer here before the transmission cables and just after the power station. So, wait, let me switch to black. There we go. Transformer X causes the potential difference to rise, to increase. I guess increase is the better word here. That voltage is going to go up. But since power in equals power out, so let's say the voltage in was 5 and the amps in was 2 amps, and let's say the voltage increases to 10. Since power is voltage times current, and this has to also equal voltage times new voltage times the new current, that current has to drop to 1. So as you can see, 2 to 1. Current needs to decrease here at X, transformer X. Now, not only does P equals VI, but using the equation sheet, we know that P equals I squared R is another solution, another equation. We use this exact equation here, P equals I squared R, to solve this one, actually. Because it looks like they're talking about power loss and current and resistance. So we can arrange for resistance for P over I squared, which would be 1.60 times 10 to the 9 all over 2000 squared. So our resistance, if we throw it into our calculator, our resistance would come out as 400 ohms. Using physics equation sheet again, we have to answer these questions. 1.4 is about linking efficiency, total energy input, and useful energy output. So we have efficiency, I'm just going to write F for short, is useful energy output over total energy input. I guess we have to use this equation here because we've given total energy input, we're given efficiency, now we need to find useful energy output. It's going to be 0.992 equals, we're going to call this N, just as the useful energy output, just replace it with a variable. It's very mathematics, a lot of mathematics here, but now we need to multiply 34.2 and 0.992. 0.992 times 34.2 will give us 33.9 gigajoules. So that's our answer, 33.9. This question is on specific heat capacity. We see a power supply connected to a joule meter connected to an iron block. We're connected to this heater that will heat the iron block. And we have a thermometer attached to the iron block as well, and we have a stop clock. The student left the thermometer in the iron block for a few minutes before recording the initial temperature. Suggest why. Well, this is so that the temperature of the thermometer is going to be the same as the iron. So we'll just write temp for short. I admit in exams do not write these short phrases and symbols, really. Just write the full word. So temperature of thermometer is the same as, just use an equal sign here, temperature of iron block. Oh, misspelled that. Iron block. Moving on. A few easy questions. Okay, now I have a graph question. These ones usually need more attention. This is calculating specific heat capacity. So, yes, you can use the fixed equation sheet, but this will come up a lot in exams and whatnot, so it's kind of good just to memorize it. Now you can use delta T here to represent temperature change, or you can use theta. We have M for mass and C for specific heat capacity, and E is just energy transferred. We know that energy transferred is 26,000 joules. We know the mass was 2 kilograms. We don't know what C is, so just write that. And the temperature change between the 5 and 10 minutes. We have to use this graph going up at 5. We come across at 28 and goes at 10. We come at 54. Alright, so we have to do times temperature change, 54 minus 28. If we rearrange for C, throw it into a calculator, we've got 54 minus 28, which is 26. 26 times 2 is 52. Then 26,000 over 52 is just going to be 500. 500 joules per kilogram degree C. That's our answer. Here they're asking us what will the effect of adding insulation have on the investigation. Well, going down the list, it's not going to be the power output, because insulation never affects power output. Temperature of the iron block will increase more slowly. No, the insulation's on the outside. Calculated specific heat capacity will be more accurate. This is true because we're reducing heat loss. So if it's more accurate, that means uncertainty can't be greater. Therefore, it's going to be this one, which would be the second one. The iron block will transfer thermal energy to surroundings at a lower rate. Yep. As you just said, the insulation will reduce energy transfer to the outside by reducing heat loss. What is meant by direct potential difference? This is just a standard question. Potential difference, polarity, doesn't change, or you can say direction. But they like these special words like polarity. Which equation links charge flow energy and potential difference? Another one you just need to know is just E equals QV. Calculate the charge flow of the 12-volt battery when the battery transfers 5,010 joules of energy. So we'll just use this equation up here. E equals QV. Our charge flow is just going to be Q. So we have essentially 5,010 joules over 12 volts to get Q, and the charge flow comes out to be, with our calculator, 417.5 coulombs. Calculate specific latent heat of fusion of water. We know that's going to be E equals ml, because usually specific latent heat of fusion of, well, any sort of equation that needs water in it. So we have 5,010 joules, which is equal to Oh, not 0.00, never mind. 5010 0.015 times by L. Because this is our mass, and that's L, and that's our energy. So L is going to end up being 5010 divided by 0.015 to give us 334,000 joules per kilogram. Oh, a 6-mark question. Okay, I like to approach most 6-mark questions with a bullet point plan of attack. So this is talking about explaining the changes in the arrangement and movement of particles as the ice melted and the temperature increased to 5 degrees C. So when ice melts, so let's talk about the arrangement first and movement. So first bullet point, as the water warms up, we get particles moving faster. It's alright, velocity increasing there in short form, but do not do this in exams. Please use good English. That means the kinetic energy also increases of the particles. Kinetic energy of the particles will rise. Now about the arrangement and movement in a solid, in the ice, the particles are arranged in regular patterns. In a liquid, they move freely, but also in liquid, randomly arranged, or we can just call it random arrangement. That's what the better term they want us to use. We can also say that kinetic energy of the particles plus their potential energy, some of that is just their internal energy. I'll probably give you a mark, honestly. And do we have 6 bullet points? I think we do, but let's throw in another one. Let's throw in no, I think okay, I think we can just leave it as it is. There's no point overachieving. They just want 6 good bullet points, 6 marks. And let's leave it like that. Oh, got a 4 mark, and it's on probably, okay, now that I've seen this, it's definitely on MGH, change in gravitational potential energy. So we're given that the mass is 2,500,000 kilograms of water, and the change in the potential energy, gravitational potential energy, is 367.5 megajoules, sorry. G is 9.8, yeah. And calculate mean change in vertical heights. So we got 367.5 times 10 to the 6 to be equal to 2,500,000 times 9.8 times h. I should probably write down the equation first to make it clear to the examiner what we're doing. And this is basically what we're doing. So we can rearrange for h to be gravitational potential energy over mass times gravity, and h will come out to, if we throw it into a calculator, one sec guys, h is 15 meters. It's kind of surprising. It's a whole number. Usually it will be like a 14.7 or something like that, a decimal, but it says 15. I'm going to trust my calculator. Okay, moving on to the next question. We're nearly coming to the end of part 1 of this paper. I'll be uploading part 2 either later today or tomorrow. Looking at this question, we have 3 kilowatts of electrical power transferred by the generator. Time taken to transfer it all. That's what we need to look for. This is how much energy is transferred. Use the physics equation sheet. Give your answer in standard form. We know that power equals energy over time. So I suppose it's just 2.16 times 10 to the 7 over the power. Don't forget to convert the units. It's in 3 kilowatts. Convert it to watts by timesing by 1,000. So if we throw this into our calculator, which I'm trusting again, I'm going to get 7,200. Oh, nearly made a mistake. It's in standard form. So it's actually going to be 7.2 times 10 to the 3 seconds. So I suppose it seems very straightforward, this question, only using one equation for 5 marks. I guess your mark is just for knowing what the equation is, rearranging it, converting into standard form, and converting kilowatts to watts. Those are probably your key marks. Okay, we have a graph that shows the power output of the generator varying during 1 year. Power output against the month. Solar power system is installed. Cool. Explain why this improves the reliability of the electrical supply to the village. Okay, improving reliability. Okay, I see. So this solar power system, using this, it will probably have a greater power output than the hydroelectric one, I think. Because the if we look here, it kind of dips like at this end of the graph. So greater power output than hydroelectric generator. And therefore there'll be, just use the maths symbol for therefore, because also just short form. Therefore less variation in total power output. Guys, there's some music playing in the background because, well, my neighbors are just partying for some reason, and it's not even partying at 11 AM. That's weird. Anyways, next question. Comparing the structure of a carbon-14 atom to a carbon-12 atom, both being isotopes of carbon. We know what isotopes are. They just have the same number of protons. Therefore, to balance charge in each atom, they should also have the same number of electrons. But isotopes, what do we know about them? Well, they're one difference, since we have to compare. We have to pull up both similarities and differences. Their one difference is that they will have different number of neutrons. And those are your 3 points to get those 3 marks. Carbon-14 is a radioactive isotope. Yeah. It has a half-life of 5,700 years. What does a half-life of 5,700 years mean? There are several I think there's like 6 definitions of this half-life, but I liked using the activity one. So it's going to be the time taken for activity of a radioactive sample to halve. In this case, it's 5,700 years. Moving on, Oh, we're flying through this. Sample of fluorine-17 has an activity that is 1/4 of its original activity. Calculate the age of the sample of fluorine-17. So if it's 1/4, so say its original activity, okay, we have 1. Half-life is responsible for bringing it down to a half, then bringing it down to a quarter. That's essentially what half-life does. So we've essentially gone through 2 half-lives here. So if we take this fluorine-17, 64.37, multiply it by the number of half-lives. Remember, this is just for one half-life. How many seconds in one half-life? 64.37 times by 2, you get 128.74 seconds. You can also write, I guess you can write 129 if you want to do 3 sig figs, but I'm just gonna write down what's on my calculator, because I guess it's just safer. But yeah, you can write just 129 seconds. All the isotopes in Table 1 emit beta radiation. Explain which isotope would cause the biggest risk to a person's health based only on the half-life of each isotope. So based only on the half-life of each isotope. Well, it's going to be nitrogen-18. So it's going to be nitrogen-18. It has the smallest half-life and therefore greatest activity. And therefore, if a greater activity essentially means a greater dose of radiation per second, because it's technically greater rate of dose of radiation, and that rate basically means per second. Greater dose of radiation per second absorbed by the person. But yeah, because it is a risk to the person's health because the radiation is very easily absorbed. It is beta radiation, so yeah, it has very mild ionizing power in the mid-range. That's more than enough to get inside your body. Describe the difference between irradiation and contamination. Okay, yeah, I thought this would come up in the paper, and it did eventually. Irradiation is just the exposure to radioactivity, and contamination is just like the unwanted, like you don't want it to be there, the unwanted presence of unwanted presence of, sorry guys, I'm stuttering, unwanted presence of radioactive sample or material. To get this marking point for radiation, you have to mention like a person, because the question is concerning people who work in the nuclear power industry. So exposure to radioactivity to people or a person. Okay, that's 2 marks there. 2 marks that you really have to think about, honestly. You have to give it a lot of thought on how to write these 2 bullet points, because the wording is very, very precise. Give 1 health risk to a person working close to a source of nuclear radiation. We know it gives rise to tumors and several forms of cancer. It's one of the greatest health risks that we have to consider. A worker stands 1 centimeter away from a radiation detector. The amount of radiation the worker emits is recorded. Explain why the worker needs to stand close to the radiation detector. But if it's 1 centimeter, I'm thinking of alpha radiation. So some may be emitting alpha particles, therefore alpha radiation. And we know about alpha radiation that it has a very short range. This is what I thought as soon as I saw this 1 centimeter away from radiation detector. Usually it's like a centimeter in air, that's their maximum range for alpha particles. Okay, another 2 marks done. This is our final question of part 1 of this video. The daily dose caused by working in a nuclear power station is this many millisieverts. And the hourly dose is this many millisieverts. Okay. For cosmic rays to a pilot and worker in a nuclear power station. Cool. Calculate the number of days it takes for a nuclear power station worker to receive the same dose as a pilot flying for 24 hours. So take this hourly dose of the pilot and multiply it by 24 to get the dose in a day. Using my trusty calculator, I get 0.072 millisieverts a day, and then if this is the daily dose, then we take this amount, because this is per day, and we divide it by the daily dose of the worker in the nuclear power station, and we should get 144 days. Wow. So this basically means that the worker in the nuclear power station they have to be working there for 144 days to experience similar doses to the pilot